So many things. All right, so let's go ahead and get started here. So we're given a couple functions which each on their own have restricted domains. If we're looking at this one just to kind of remind ourselves what's happening, this function f of x, we know that the insides have to be bigger than or equal to 0. And if I was trying to solve the inequality, I would just move the x to the other side and say, okay, great. 6 is bigger than or equal to x. Or in other words, x is less than or equal to 6. I'm not going to write up the domain like in interval notation. This is just kind of for my own use. In a similar way, from this function here, I can see that, okay, the x plus 2 has to be bigger than or equal to 0. So x has to be bigger than or equal to -2. Again, that wasn't asked of us. I'm just kind of thinking about it so I can help myself do the next part of the problem. So for the domain of f of x plus g of x, well, f of x plus g of x is nice and easy. It's just that plus that. It's the square root of 6 minus x plus the square root of x plus 2. And maybe, unfortunately, there really isn't a way to simplify that. It just is what it is. There's no simplifying. You're stuck. Fine. As far as finding the domain, we can kind of see that, well, we have to really satisfy both things, right? To be in the domain of this sum of functions, we both have to be less than 6. I should say x has to be less than or equal to 6 and bigger than or equal to -2. If we're too negative, like -3, this part here isn't going to be defined. If we're too positive, like +8, this part here is not going to be defined. So we're kind of stuck being in between. Another way to see this is using the number line. And we'll use, let's see, we have a +6 and a -2. And in red over here, I should have made these different colors. Oh, well, I didn't. So over here in red, here's the domain of f. Everything less than or equal to 6. And over here in purple is the domain of g. Everything bigger than or equal to -2. And for the domain of f of x plus g of x, it's going to be where they overlap. I should have used purple, red, and blue, and then made purple, but I wasn't thinking ahead. So, we're going to get the overlap of them. Everything between -2 and +6, inclusive of those endpoints. So here the domain is going to be the inclusive interval from -2 with a bracket to +6 with a bracket. I'll point out that any other combination with one exception. So actually, when I say let me back a little bit. So we have all sorts of ways of combining functions together arithmetically. Like we can add two functions, or subtract them, or multiply them, or divide them. Just like usual operations between numbers. And for addition, subtraction, or multiplication, the domain would be the same. So if we subtracted these two functions together, still would have the same domain. If we multiply these two functions together, even though you might be able to simplify it and get other stuff, originally the original expression would still have the same domain, right? If I write this multiplied by that, I still need x to be less than or equal to 6 and bigger than or equal to -2. And if we divide them, the domain is almost the same, except we have to look out for the possible division by 0. So here, when we divide these two functions and say that f of x divided by g of x is equal to, let's see, f of x was that one, the square root of 6 minus x divided by the square root of x plus 2. I don't really want to simplify that at all if I'm talking about domain, even though I could write that as 1 square root of 6 minus x divided by x plus 2. But I still want to see where or what values of x make this thing defined. Well, we still need x to be less than or equal to 6. And we still need x to be bigger than and not equal to -2. Right? If it was equal to -2, we'd end up dividing by 0. So here, it's almost the same as this, except we want to exclude the -2 right there. So our domain here is going to be everything from -2 exclusive to 6 inclusive. And if we inverted them, I should say, no, invert's fine. There's a better word there. If we took the reciprocal, if we did g divided by f instead of f divided by g, we'd end up including the -2 and excluding the +6. So whether you're adding, subtracting, multiplying, or dividing functions together, their overlap domain essentially stays the same, except for the division part where it's just slightly different because you're usually excluding one or two of the endpoints. Oh, another word for this overlap is the intersection of these two domains. So this overlap here, overlap is also called the intersection of the domains. Just a reminder, you're always welcome to ask questions if you have them. Last class, a couple people came up after class and asked questions like, oh, these would have been great questions to have asked during class because everybody would probably have liked to have asked or heard the answer to that. So if you have questions, really, I know I kind of go at a quick pace, but you're welcome to make me stop and say, hey, James, I have a question about what you're saying because there's probably questions. There's probably questions about the last one here because this last thing is a different way of combining the functions than adding, subtracting, multiplying, or dividing. This is the composition of functions, f of g of x. As I read this, I think of, oh yeah, question. Yeah. Sure.
X plus 2 is greater than equal to 0. Don't you have to change this?
I don't have to change the sign unless I'm multiplying both sides or dividing both sides by a negative number. To do this, all I did was subtract 2 from both sides, and that doesn't require me to change the direction of the inequality.
Oh.
There's actually one, well, there's one other thing too there, but that's, I'll say that for later. It's not important right now. So for the domain of f of g of x, let's actually write out what f of g of x is. So f of g of x, I kind of like to work from the inside out, but it doesn't really matter which way you do it. I'm thinking of this as f of, well, let's see, g of x is the square root of x plus 2. And then the function f, which is written up here, right? F of x is the square root of 6 minus x. So when I have f of something that's not just x, here's what I like to do. I know that f of x is equal to the square root of 6 minus x. F of something else is going to be the square root of 6 minus whatever's in the parentheses. I just like to write a blank parentheses there and then fill it in with whatever is the input of my function. So then that's going to be 6 minus the square root of x plus 2. And kind of like all these other problems so far, I don't really need those parentheses there. That's not what I was going to say. Sorry, I got distracted. Like all these other problems, there's really no simplifying. It is the square root of 6 minus the square root of x plus 2, and there's nothing else to be done there to make it nicer. It is what it is. To find the domain, there's a couple things I would encourage you to think of here. First and foremost, for compositions, we always have to obey the domain of the inside function. So in this case, g is the inside function. Its domain automatically gets obeyed, meaning for sure, we need that x plus 2 is bigger than or equal to 0, or x is bigger than or equal to negative 2. We have to obey that. There might be other restrictions as well, but definitely we can't pick numbers for x that are less than or equal to less than negative 2. Right? If we pick negative 3, we'd have negative 3 plus 2, which is negative 1, and the square root of negative 1, not real. But then there might also be additional restrictions we have to look for. So if we look at the bigger function, we see, oh, well, I have another square root, and we know that the stuff inside the square root can't be negative. So we're going to also say that this argument here, 6 minus the square root of x plus 2, has to be bigger than or equal to 0. What that means for us is x can't be too big, right? If x was like, I'm going to pick a number here. If x was 47, 47 plus 2 is 49, and the square root of 49 is 7, and 6 minus 7 is negative, and we want it to be not negative. We can solve this inequality, but we have to be a little bit careful here. So we're going to add that to the other side, say 6 is bigger than or equal to the square root of x plus 2. And then we can square both sides since we already know both sides are positive. It's a little dicey here, but we're paying attention. 6 squared is 36. The square root of something squared is just the something. So square root of x plus 2 squared is just x plus 2. And then if we subtract it from both sides, we get that x has to be less than or equal to 34. If x was any bigger than 34, that'd be problematic. Sometimes you can kind of go the wrong way here if you're not careful with your squaring, but that's a tale for another day. So we need both x to be bigger than or equal to -2 and less than or equal to 34. So writing it as an inequality, we need x to be less than or equal to 34, bigger than or equal to -2. Written as an interval, we have our domain as -2 with a bracket to 34 with a bracket is our domain of f of g of x equal to the square root of 6 minus the square root of x plus 2. Yes. Did I say so that yes it does. Or you mean bigger than not equal to? Or just bigger than? So I would say that that's what I've written right here. That x is bigger than or equal to -2. It's just written in kind of the opposite way. So I would point out that these two expressions say the same thing. This one says that -2 is less than or equal to x. And if you multiply both sides by -1, no, that's a bad. Don't, James. What are you trying to say there? No, you could. It's hard rewriting. It's yeah. I mean, you could do it that way, but it's terrible. Yeah, you could multiply both sides by -1 and say that 2 is bigger than or equal to -x, and then add x to the left, and then subtract 2 from the right, and write it that way. So they really are the same thing. So I often will say -2 is less than or equal to x, or I'll write it like this, but then say it the other way because I often think of starting with x and then saying, oh yeah, x is bigger than something, or here x is less than something. Yeah. It might be, yeah, it probably is worth looking at the other composition. So instead of f of g of x, let's explore g of f of x for just a couple minutes. And then we will move on to other things. So if we look at g of f of x, well, again, working from the inside out, that's going to be g of the square root of 6 minus x. And then g was this, I should say, just as a reminder, g of x is the square root of x plus 2. So g of some stuff is going to be the square root of blank parentheses plus 2. And then inside the parentheses is what's inside the parentheses here, which is the square root of 6 minus x. Just like the previous composition, we have to obey the domain of the inside function. So we must obey that 6 minus x has to be bigger than or equal to 0. Or in other words, x is less than or equal to 6. Or if you prefer to write it as 6 is bigger than or equal to x, same thing. So x can't be any larger than 6. It has to be 6 or 5 or pi or -2 or whatever. But then we have to look at the bigger function. And now here's where things can kind of go sideways. If we don't look at this with a careful eye, we can make a mistake here. So let's avoid the mistake. When you take a square root of something, like a nice square root, what kind of outputs do we get? Like what's the square root of 49? Right? Not -7, 7, +7. Whenever we take a square root, the output is always non-negative. You can get 0 or any positive real number, but you can't get a negative real number. Which means this part's always positive. Or I should say non-negative, right? It could be 0. But a non-negative number plus 2 is always bigger than or equal to 2. And I can take the square root of any number that is bigger than or equal to 0. So this quantity inside here can't ever be negative, no matter what x is. X is restricted to being less than or equal to 6, but that's it. We don't have any other worries, right? This quantity, the square root of 6 minus x plus 2, if we need that to be bigger than or equal to 0, well, it is for any x that's allowed. Right? You can pick x equal to -1,000, and then 6 minus -1,000 is positive 1,006. The square root of 1,006 is 30 something, and 30 something plus 2 is for sure bigger than or equal to 0. So there's no issues here. The thing I want to point out why this is something to be concerned about is if you didn't see that, and just started trying to solve this inequality, you would end up getting some wrong information. If you try to solve this, say I bring the negative 2 over there, or I subtract it from both sides, and then square both sides. Sure, negative x bigger than or equal to 4 minus 6 is negative 2. X is less than or equal to 2. I don't need that to be true, right? I don't need that restriction. It's totally fine for x to be 3 or 4 or 5. This is leading me to bad places. So we have to be a little bit careful when we're looking about domains of compositions of functions. We have to be thoughtful about, okay, well, especially with square roots, if I'm squaring a square root, we need to be extra careful and recognize that, oh yeah, this part here, this is already bigger than or equal to 0 without any work needing to be done. Yeah.
Does that mean that the function couldn't represent any number between 0 and 2? Or
The function, like, we couldn't get an output that was 0 or 2? No, we could. This is really just, I mean, this doesn't really tell us anything, to be perfectly frank. We certainly could get 0. We could get 2. Yeah, we could get 2. Sure. We could certainly get 2 if we let x equal 2, which is kind of funky. Because if x was 2, 6 minus 2 is 4. The square root of 4 is 2. 2 plus 2 is 4. The square root of 4 is 2. So many 2's and 4's. So yeah, so it's not really, I don't think it's giving us any information. All right. Enough domain for now. Yeah, enough.
what is the domain of blue?
Oh yeah, fair enough. So that's an excellent point. When you're doing a problem like this, it's always good to make sure when you're done that you've answered the question that was being asked. I haven't here. Not really. So I should go back and say, okay, yeah, the domain of f of g of x equal to the square root of the square root of 6 minus x plus 2. Well, all we had to do is say that x was less than or equal to 6. We have to obey that inner domain. So here our domain is everything that's less than or equal to 6. So negative infinity up to 6 inclusive. Whenever I find a domain, at least in the beginning, I kind of like to check by plugging in a few values of x. I'm like, okay, yeah, if x was 5, totally fine. If x was negative 3, totally fine, right? Any kind of number in there works. It's good to think about just mentally testing a few points to see, oh yeah, those values are legit. We don't need to worry about having the wrong things here. Yeah, good questions. Always, especially with word problems, and like when we start talking about in the future related rates and optimization, it's a really good idea to, once you think you're done, go back and read the question again and make sure you've answered the question that's actually being asked. Yeah, myself included. So what's next on the docket? Oh, yeah, sure. Piecewise functions. I have so much to say. Not enough time. But let's look at a couple examples of piecewise functions. So here's an example. Here's an example I don't love. Let's look at this example I do like. Let's say our function is the following. F of x is equal to x squared minus 1 when x is less than negative 2. It's equal to the square root of 4 minus x squared when x is bigger than or equal to negative 2 and less than or equal to positive 1. And finally, interesting choice, James. It's equal to 3 to the x when x is bigger than 1. Most of the time with piecewise functions, we usually graph them. Like kind of the whole point here is just to really see what this graph looks like and see how you graph a piecewise function. A little bit later on, when we talk about limits, we often use piecewise functions as examples of functions where limits end up not existing. They're kind of our go-to example, which is really why we're talking about them, to be perfectly honest. But let's graph this. We're going to graph f of x. And what we're really going to do is we're just going to graph each part. So we're going to graph all 3 pieces by themselves, which is kind of not the way I would usually do it. But let's start off by doing that. So let's graph y equal to x squared minus 1. That's a typical looking upward opening parabola shifted down 1. We're taking our usual y equals x squared. and shifting it down 1. So we have a vertex at 0, -1. It looks kind of like this. There's our y equal to x squared minus 1. And then what I like to do if I'm doing it this way, where I'm kind of, let's save it actually. I'll hold off on that for a minute. See, I gotta save myself some space to draw the actual piecewise function here in a minute here. Let's graph y equal to the square root of 4 minus x squared. What kind of shape is that? I ask this because it actually is a very well-known shape. It just might not look like it from the get-go. If you square both sides and then add x squared to the left, it might look a little bit more familiar. X squared plus y squared equal to 4 is a graph of a circle. This part here, y equal to the square root of 4 minus x squared. Well, we all just said, you all said that when you take a square root of something, you only get what kind of numbers out? Positive. So we're not going to get the bottom half of the circle because we can't get any negative output values here. So this y equal to the square root of 4 minus x squared is the top half of a circle or a semicircle. And it's the top half of a circle with radius 2, center is the origin. So it's going to look like this. Thirdly, y equal to 3 to the x, which actually is kind of the next section we're going to talk about, but we'll get a head start here. So graphing y equal to 3 to the x, 3 to the x, or 2 to the x, or 5 to the x, or any positive number raised to the x power is an exponential function. It has the usual exponential shape, which I'll show you. Usually these graphs have an intercept at 0, 1, a y-intercept at 0, 1, and they look like this. They get steep very fast. I probably undersold how steep this graph gets. If you graph this on the graphing tool like Desmos, you'll see that it kind of like looks like that, like you're going up super duper fast. I usually don't plot a whole lot of points here. I might plot the point like 0, 1. I might choose one other point like 1, 3. You could go on and on, right? If x was 2, you get 9. If x was 3, you get 27, and so on and so on and so on. But the y values get really, really large, really, really fast.
So for y equals 3x.
3 to the x. So I would encourage all of you, and I'm maybe a little bit of a stickler for this in general, but I think it's worth your while to say all the words. 3 to the x, f of x, sine of x. I think those that of word especially super duper important. Not to interrupt you there, but just I want to point out that those are important. So yes, for this one,
So for y equals 3 to the power of x, the y-intercept would be still 1.
correct. Yes. We'll address that in a moment, but let's graph this first. So then what I would do if I was actually, so normally what I would do is actually wouldn't graph all 3 of these. What I would really do is I would just graph the parts of each of these I need on the same graph. So I would have started by graphing this one up until where x is -2. So there's -2 right there. And I would have had everything to the left of -2. Because if x is less than -2, it is left of -2. For this piece in the middle here, x is between -2 and +1. There's -2, there's +1. I want the graphical part from there to there. And then, oh, and maybe I want to know that if I plug in 1 here, that's kind of gnarly. I get 1 comma square root of 3. Okay. Over here, if I plug in -2, I get -2 comma -2 squared minus 1 is +3. A lot of 3's showing up. And then over here, I want this part of the graph where x is bigger than 1. So I want everything to the right of 1. So all that. So those scribbly parts, those are the 3 pieces that are going to make up my actual piecewise graph. So let's see here. 1, 2, 3. So 4. Starting at -2 and x value -2, my y-intercept, my y value, sorry, is +3. And then it's just the left part of that parabola. It kind of looks like this. Not my best picture of it. Sorry. Then for this middle part, we want everything from -2 to 1. So we have, I made a small mistake. So I should not have filled in this circle here, right? Because we want this portion of the graph when x is less than -2, meaning it doesn't actually get to -2. So that should actually be an open point right there at -2, 3. It's not included, right? If x is closer and closer to -2 from the left, like -2.1, -2.01, -2.00001, like just a little bit left of -2, the y values are getting really, really, really close to 3. But they're not actually getting to 3. And then as we move to -2, we're going to get this middle piece. So we do have this part filled in here. And then we're going to go over here. And then we're going to end it about right there. So it's going to look like that. Top half of the circle, ending at the point 1, √3. Everyone's favorite number, √3. Yeah, okay. And then finally, this last piece over here, we want the right part of 3 to the x starting when x is 1 and y is 3. So we're up here, open circle, because we don't actually get that point, because it's x is bigger than 1, not bigger than or equal to 1. And then it looks like that exponential thing over there. Oops, sorry, you can't quite see all that. Apologies. If I'm ever off screen, you guys want to see it, just let me know and I'll scooch it the appropriate way. So there's our piecewise function graphed out. I would make a couple comments here. It is very discontinuous. We haven't talked about continuity yet, but I would just point out that if you tried to draw this graph, you would have to lift your pencil off the paper, and that's kind of the easy way of describing whether or not something is continuous. If you can draw it without lifting your pencil off the paper, it's continuous. If you can't, it's not. There's a more formal definition, which we will get to eventually. Yeah. Why is it √3? Good question. So when I plug in 1, I'm plugging it into this middle piece of the function. 1 squared is 1, 4 minus 1 is 3. I get the square root of 3. Yeah. Other questions? Okay. Time is fleeting. So two things. Yeah. Thing one. Let's graph another piecewise function. Here's one that might be, well, I'm going to make it like this. Sure. G of x is equal to -x when x is less than 0. Positive x when x is greater than or equal to 0. I want you all to try graphing this on your own. So I would start off by graphing y equal to x, y equal to -x, and then try putting the pieces together that we need. So there's the two graphs of the pieces of the piecewise function, y equal to x and y equal to -x. But then we want to make sure we get the right parts. So for y equal to x, which is the second part here, we only want it when x is bigger than or equal to 0. So here's x equal to 0, and we want the right side of it. We want all of that. None of that. Similarly, for this piece here, we want y equal to -x when x is less than 0. So we don't want to include the origin, but we want everything to the left. And just to be perfectly clear, when I think about X being less than something, I think about it being left of something. Less than is left, greater than is right for X. For Y, it's top and bottom, right? If Y is greater, it's up. If Y is less, it's down. So then I want these two pieces. Cool. Well, look, they're going to meet up at the origin. Even though this left piece is missing the origin, this right piece is going to fill it right in. So it's going to look like what I hope is a familiar looking graph. G of X is the absolute value of X. If X is positive, you get the same value back. If X is negative, you get the corresponding positive value back. And you can write it in three different ways. You can write it as the absolute value of X. You can write it as this piecewise function. Negative X when X is less than 0, and positive X when X is bigger than or equal to 0. And it doesn't actually matter where you put the equal to part. You can put it here or there. And finally, as I think we saw on Tuesday, you could also write this as the square root of X squared. Kind of neat. It definitely is a function that comes up relatively often. So it's good to know that when you see an absolute value function, there is a way of expressing it as a piecewise function, which definitely does become necessary when we start talking about finding the derivative of this function. All right. So piecewise functions, they're useful. We'll probably talk a bit more about them when we circle back around to limits, but there's lots of other things to say. So we'll continue on. So let's go ahead and talk more about exponential functions. I know what I was going to say. So let's graph a few things. Let's graph first and foremost f of x equal to 2 to the x. Kind of my favorite, second favorite exponential function. We're going to plot a few points just to make it really kind of precise, and then we'll talk about how you don't really need to do that. So if I was plotting some points, I'm going to make a little table. I'm going to pick some convenient x values and then fill in the corresponding f of x or y values. So the values I'm going to pick for x are 3, 2, 1, 0, -1, -2, and -3. So then f of 3 is going to be 2 to the third, which is 2 times 2 times 2, which is 8. And f of 2 is going to be 2 squared, which is 4. F of 1 is going to be 2 to the first, which is 2. F of 0 is going to be 2 to the 0, which is 1, which I kind of want to talk more about. F of -1 is 2 to the -1, which is 1 over 2 to the first. F of -2 is 2 to the -2, which is 1 over 2 squared, which is 1 over 4. And f of -3 is 2 to the -3rd, which is 1 over 2 cubed, which is 1 over 8. So, yeah, I think it's worthwhile for just a second here. Before we continue graphing this, I just want to point out or address the question that you might have. Why is 2 to the 0 equal to 1? Well, the unsatisfying answer is because we need it to be. It has to be. The more satisfying answer is because there are rules of mathematics that make it so. The specific rule I'm referring to is what's called the additive law of exponents. So if you took something like 2 to the third and multiplied it by 2 to the fourth, what does 2 to the third mean? I know that equal to 8, but what it means is 2 times 2 times 2. So 2 to the third is 2 times 2 times 2. And 2 to the fourth is 2 times 2 times 2 times 2. How many 2's are we multiplying together? How do we get 7 from 3 and 4? We add them together. So this is the same as 2 to the 3 plus 4, which is 2 to the 7th. That's the additive law of exponents. When you multiply two things together that have the same base, we can just add the exponents because you're just really counting up the number of times you're multiplying that base together. But then when your numbers become things that aren't nice positive integers, well, like what's 2 to the 1.5? Multiplying 2 by itself 1.5 times, that seems like a weird thing. Well, here's what's happening. Or let's talk about 2 to the 0 first. If I took 2 to the 0 and multiplied it by 2 to the third, Well, the additive law of exponents says I get to add the exponents together. 0 plus 3 is 3. Okay, so I have 2 to the 0th multiplied by 8 is equal to 8. There's only one choice for what 2 to the 0 gets to be. It has to be 1, because the only number multiplied by 8 that's still equal to 8 is 1. That number there must equal 1. There is no other option. If we want this rule to be true, right? If we're all in agreement that the additive law of exponents needs to be true, which it does, then the result is that 2 to the 0 has to equal 1. There's no other choice. That's also where fractional exponents come from, or at least this idea. Like if you want to find, say, 9 to the 1/2, well, you might know that that's the square root of 9, which is 3. But the reason it's actually going to work that way is because, well, if we use the additive law of exponents, what's 9 to the 1/2 times 9 to the 1/2? What's 1/2 plus 1/2? So we get 9 to the 1. So we have a number multiplied by the same number equal to 9. The number has to be 3 if we're assuming it's positive, which we are. Right? Must be 3. There is no other choice. So that's why when we say something is a fractional power, we also write it as a square root. And you can make a similar argument for like the, sure, 8 to the 1/3 power is the same as the cube root of 8. Because 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3 is 8. That means 8 to the 1/3 has to be 2, because 2 times 2 times 2 is 8. It's kind of neat. Anyway, back to graphing exponential functions. You might notice here that as x gets more and more negative, these values get smaller and smaller and smaller, but they stay positive. Right? If x was like negative 100, you get 2 to the negative 100, which is 1 over 2 to the positive 100. 2 to the 100 is a really big number. 1 divided by that is a really, 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 really small positive number. Very close to 0. So when we graph this thing, three, four, five, six, seven, 8. So we get the point 0, 1, and 1, 2, and 2, 4, and 3, 8, and negative 1, 1/2. And I'm not going to plot the rest because it starts to look messy. It's going to look like this. There is your prototypical exponential function. Let's write down some of its qualities. Its domain. Nothing's off limits. There's no denominator we have to worry about dividing by 0. There's no square roots or even roots where you have to worry about taking a square root of negative, and there's no logarithms. So here our domain is everything, all real numbers. The range, we can graphically see. The y values get really, really high, and then they go as low as almost 0, but not 0, right? We can't ever actually get to 0. So our range here is 0 exclusive, and then as large as you want positively. A couple other notes I would make about this function. It's definitely continuous, even though we haven't defined that. And it's also differentiable. Again, something we haven't defined yet. For now, when I say those words, or when you think of those words, I would encourage you to think of continuous means we can draw it without lifting our pencil off the paper. And differentiability, although I'm kind of fudging it a little bit here, but if a function is smooth, it is differentiable. So a good counterexample would be this previous function. Definitely continuous, definitely not smooth. It is pointy right there. If your function is pointy somewhere, it's not continuous there, typically. No, I said the wrong word. If your function is pointy somewhere, it's not what? differentiable there. It's definitely continuous there in this case, not differentiable there. Don't hesitate to call me out. Sometimes they say the wrong thing, not on purpose. Sometimes they do say it on purpose, but I'm super obvious about it. I'm like, what do you think about that? So yeah, if I say something and I'm being obvious about it, you should also say something. The other thing I want to point out is this function is increasing. All that means graphically is from left to right, the y values get higher. Function is decreasing if from left to right, the y values get lower. There is like a formal definition of it, but it's not super important. No, yeah, I don't think we need to write that down right now. Oh, and one last thing. We have a horizontal asymptote, and it's y equal to 0. That just means that as you go either all the way out to the right or all the way out to the left, the function gets closer and closer and closer to that particular y value. In this case, it's to the left. All right. The good news is pretty much all the exponential functions look like this. So if I was going to graph something like y equal to 3 to the x, it'd be pretty much the same. And I wouldn't do all this work of plotting all these points. What I would do is say, okay, well, in fact, we already graphed this one, but I would just do this. Got the usual shape. The point there is 0, 1, drawn not super well. And that's kind of it. Right? Like there's not a lot else to say about this. It's got a horizontal asymptote, y equals 0. That's all I really care about.
So what if it was y equals 1,000 to the power of that?
Sure. Well, yeah, you're going to be disappointed. If I was graphing y equal to 1,000 to the x, I might draw it slightly more steeply. The problem is if you try to graph this accurately, it's going to look really stupid. Stupid is the wrong word. It's going to look not very helpful. Here's what I mean. Oh, come on, get out of the way. Sorry, one sec. So if you graph y equal to 2 to the x, oops, not 2 to the second, 2 to the x, it looks reasonable, right? It's got kind of a nice usual exponential shape. And if we zoom out a little bit, okay, we can see it's getting big pretty fast. On the other hand, if your base is big, let's even 20, starts to look kind of just like very vertical. And if you do something really large, like 1,000, it almost looks like you're just taking a sharp turn like that. So graphing this accurately on paper just starts to look kind of silly. So that's why all my exponential graphs usually just look kind of the same because they all still have the same usual shape and they're doing whatever we want. Now, the nice thing about graphing things on your own is you don't have to graph things to scale. You can label this thing however you want. So if this is the point 0, 1, cool. Here's the point 1, 1,000. Yes, it's not to scale, but am I displaying the information that's important? I am. I hesitate to say only. There's 2 more exponential graphs I'd really like us to think about for a second here. Yeah. First of all, yeah. F of x equal to 1/2 to the x. Now let me turn that. I hate the little button there. There we go. Cool. This is also an exponential function. I will point out for exponential functions, your base really does need to be greater than 0. If it's negative numbers to weird powers are not always well defined. And your base shouldn't be 1. Because 1 to any power is just 1. Right? 1 times 1 times 1 times. Oh, yeah, it's just 1. But here our base is less than 1, meaning if x gets bigger, the output's actually going to get smaller. Right? 1/2 to a large power, like, for example, f of 4, which is 1/2 to the 4th power, is 1/2 times 1/2 times 1/2 times 1/2, which is 1 times 1 times 1 times 1 over 2 times 2 times 2 times 2. It got small. So when your base is smaller than 1, your graph actually flips around the y-axis. In fact, you could actually rewrite this as 2 to the negative 1 raised to the x power. And when you have a power to a power, you get to multiply those powers together and say that that's going to be 2 to the negative x. And putting a negative sign on the input gives you a reflection around the y-axis, right? We're essentially changing all of our x values that were positive to negative and negative to positive. So you're switching the graph like that. So I shouldn't turn around like that. So then our graph is going to look like this. All the same properties, same domain, same range, same asymptote, same y-intercept, but this one is decreasing instead of increasing. So this graph is decreasing. Okay. And then there's one more that's probably the most important one. Probably, maybe, I don't know. It's a matter of opinion. F of x equal to e to the x. So e is a super important number. It comes up all the time. It's referred to as the natural base. All we really need to know is that e is approximately 2.7. That's it, really. As far as we're concerned, yes, it's a number. It's an important number. Comes up a lot, but it's just about 2.7. Between 2 and 3, closer to 3. So when we graph it, or should I say, when we graph the exponential function here, it should kind of live between the graphs of 2 to the x and 3 to the x. We don't really need to do that when we graph it, but that's kind of how I think about it. In fact, just so you all can see it, so you all can see a nice version of it. Oh my gosh, so many things. So, right, if we actually look at 2 to the x, and then we graph 3 to the x. So let's zoom in just a little bit here. So we can see they do cross each other at the y-intercept, which is typical. And then if we graph y equal to e to the x, it is indeed between those two graphs, as it should be. And it's kind of a very important graph. I will say one way that people talk about this graph is that it's the only exponential graph whose slope at the y-intercept is equal to 1. What I mean by that is if you plot the line or graph the line y equal to x plus 1, which has a slope of 1, that is exactly the slope of the line that is tangent at that point right there. And it's the only exponential graph that has that quality. It's also got lots of other cool properties we'll talk about later. So yes, I should graph it because I should. But again, it's going to look like almost every other exponential graph I've already graphed. I'm trying to make it look a little bit nicer. There it is. Y equals e to the x, f of x equals e to the x. Still has an intercept of 0, 1. Still has an horizontal asymptote of y equal to 0. Still has the same domain and the same range as every other exponential function we talked about. Yes.
Would it be 1 comma for the?
Yes. If I was plotting another point, I would choose to plot the point 1 comma e.
2 comma 2e?
It would not be 2 comma e squared, which is about 8. So yeah, so if you go over another one, you're getting way up here at 2 comma e squared. And so on and so on and so on. Okay. Let's see. Where am I at here? I'm trying to get to something that I think is important for you all to see before the weekend, because I don't get to see you all again until Tuesday. So yeah. Yeah, I think we'll get there. Okay. So one of the reasons we mainly talk about exponential functions in this class is because we talk a lot about exponential growth and exponential decay. Because a lot of things in the world grow in a way that can be modeled exponentially or decay in a way that can be modeled exponentially. So let's look at a couple of examples of that. Yeah. So exponential growth and decay. Here's an example. I don't know why I'm putting a number there. That's an EX in case you're curious about what I might have tried to write there. EX, for example. A bacterial, sure. Bacterial culture starts with 10 cells and doubles every 20 minutes. How many cells would there be? In 4 hours. Well, we could figure this out kind of just in a brute force sort of way, right? If we're doubling every 20 minutes, then we're going to double what, like 12 times, I think. So you can just double, right? That's one way you could approach this. Let's actually write that out because it does show us something useful here. So here's our time, and here's our number of bacteria as a function of time. So at time equal to 0, no time has passed. We're starting with 10 bacteria. And although I can multiply by 2 easily in my head a few times, eventually it's getting kind of gross. I don't really want to write that out. I want to write it in a way that's more helpful. So after 20 minutes or 1/3 of an hour, right, because we're measuring time in hours here, I've decided. After 1/3 of an hour, we're going to have 10 times 2, which, yes, is 20. After another third of an hour, we're going to have 10 times 2 times 2, or 10 times 2 squared. After another third of an hour, which is going to be 1 full hour, we're going to have 10 times 2 to the third power. And at this point, I think we can see the pattern. Every time we go another 20 minutes or another third of an hour, we're going to double the population. So let me think about how I want to write this. Yeah, this is always the hard part. It's like, okay, well, let's say I want to figure out how much there was after, say, 2 hours. I'm going to skip the intermediate steps here. So if time is 2 hours, well, I've doubled how many more times? 3 more times, right? Because I've had 3 more. And so I'm going to have 10 times 2 to the 6th. And if I go to 3 hours, I'm going to have another double, double, double. Not in and out, right? So that's doubling 3 times. We get 10 times 2 to the 9th. If we do another hour, which is 3 more doublings, we're going to get 10 times 2 to the 12th. We could probably even write a function based on the number of hours that have elapsed. It looks to me like the number of bacteria at time t is equal to 10 times, let's see. At 2 hours, we had a power of 6. At 3 hours, we had a power of 9. At 4 hours, we had a power of 12. At 5 hours, we have a power of what? 15. 6 hours, a power of 18. It looks like you're just taking the number of hours and multiplying by 3, which makes sense because in 1 hour, you get 3 doublings because a doubling happens every third of an hour. So that looks like a pretty good formula for the number of bacteria at time t. And look, it's an exponential function. Yes.
Would you need to write 3t because you're measuring in hours?
Yes, because I've decided, but again, it was a purely kind of decision at the moment. We could have said time in minutes instead, but I should be explicit here. T is measured in hours. On the other hand, if you want to do it in minutes, well, then it would look like this. And I should use something else, but I'm going to use T. And if T equals 10 times 2 to the T divided by 20. Here, T is measured in minutes. But you can see you're going to get the same result. If you pick T equal to 1 hour, you get 10 times 2 to the third. If you pick T equal to 60 minutes, you get 10 times 2 to the third. So 1 hour, 60 minutes, if you write the function a different way, still can give you the same result. It depends on how you want to write it. Sure. So. I'm out of water. Almost, kind of. All right. Doing it this way, while somewhat useful, kind of takes a while. And it cannot always be quite so easy to see what the pattern is. So there's another way to go about this, which is to say, well, we're going to make the assumption, assume we are growing exponentially. People like to do this different ways. The way I've typically learned how to do it and done it is by saying our model of growth is n of t equal to c e to the k times t. I should say our model of exponential growth. Probably didn't leave myself enough room here. Always trying to squeeze things in. So if we have a model where n of t is equal to c e to the kt, and we know that the number of bacteria at time 0 is equal to 10, and we're also doubling every half hour. So a half hour, no, every 20 minutes. So every third of an hour. So you know that n of 1/3 of an hour is going to be 20. Or it might be more useful to say that n of 1 is equal to 10 times 2 times 2 times 2, which is going to be 80. We can use these data points to help us figure out what these constants are going to be. Usually this constant c here is really easy to find. It's almost always going to be just the value you have at your initial point if it's starting at time. So here we would say, all right, if I plug that in, 10 for n of t, 0 for t, and then k times 0 is 0, e to the 0 is 1. So I just get that 10 is equal to c times 1, so the 10 is equal to c. So now my model, my refined model, now is n of t equal to 10 times e to the kt. And then I'm going to use one of these other data points, plug those values in to find out what k is equal to. Yeah.
So if k times 0, does that cancel out?
What is k times 0? Right.
So e to the power of 0, wouldn't that be 1?
Yes.
Okay.
And what's c times 1? No pun intended, right? So if we plug in this other data point here, I'm going to use this one. I'm going to plug in 80 for the n value and 1 for the t value. Then I have that 80 equals 10 times e to the k. And then 80 divided by 10 is equal to e to the k. And then 8, which is 80 divided by 10, 8 equals e to the k. And then I'm going to take the natural log of both sides. And now I'm getting into logarithms now. Say that the natural log of 8 is equal to the natural log of e to the k, which is just k. Yes.
And breaking down what all the.
So no, not at all. So you mean this generic equation here? So typically in this equation, C is the initial population or the initial amount of stuff. So however much we're starting with at time equal to 0. K, and this is not maybe super helpful at this moment, but it is what it is. K is the relative growth rate. Which is going to become more useful when we start talking about differential equations, which is a while from now, like maybe next quarter, I think. But that's what K is. K is kind of telling us how fast the population is growing with respect to the population size. So relative growth rate, here's an easy explanation. If I said the population was growing at 1,000 people per year, not a very useful piece of information. Because you don't know how many people there are in the population, right? If I said the population of Davis was growing at 1,000 people per year, that's kind of a lot, right? There's only like 60,000 people here. 1,000 more people every year is not insignificant. If I said it was the population of New York growing at 1,000 people per year, that's way less meaningful, right? That's a very small relative growth rate. So the relative growth rate is the growth rate, 1,000 people per year in this example, divided by the population size. So the smaller that is, the slower the population is growing. The bigger that is, the faster the population is growing. That number is what that is. And again, it's not super useful here because, like, what's the natural log of 8? I don't know. Question. Good question. You mean from right here? So there's a couple ways to think about this, and this is actually kind of coming up on the next part, which is these are inverse functions. They undo what the other one does. So let me give us some room right here. So f of x equal to the natural log of x, and g of x equal to e to the x, or what we call inverse functions. They undo what the other one does. So when you compose them, meaning you do one after the other, they undo what the other one does and you get back to where you started. So if I look at, say, let's do that one first, f of g of x here, which is the natural log of e to the x, they undo each other and we get back to where we started. And I know I'm skipping a few things on purpose. Don't worry, we're going to come back to them hopefully today. And then the other direction, g of f of x is equal to e to the natural log of x, which is also equal to x. So yeah, let's finish this example very quickly, and then we'll kind of circle back around to this point here, because that is actually where we were headed next. So just to point out here, our model, now that we have both K and C, our growth model is 10e to the natural log of 8 times t. Which doesn't look the same as it did before. Right? Before we had something very different. We had 10 times 2 to the 3t. Well, we got the 10 right, but e to the natural log of 8 times t, they are the same. Here's one way to see it. E to the natural log of 8 times t, and again, I'm using a logarithm rule here that we haven't discussed. I'm going to write this as 10 times e to the t times natural log of 8. And then there's a rule that says when you have something multiplied by a logarithm, you can write that something as the power of the argument inside the logarithm. So that we can actually rewrite this as 10 times e to the natural log of 8 raised to the tth power. And then I don't like to use the word cancel here. I feel like the word cancel is generally not a great word in mathematics. I like to use the word they undo each other. Or when like 5 divided by 5 cancels to 1, I like to say it divides to 1. Or 5 minus 5 cancels to 0. I like to say they subtract to 0. So here, the e to the something and the natural log of something undo each other, and we're left with just the argument, which is 8 to the tth power. This becomes 10 times 8 to the t, which is the same as 10 times 2 to the 3t, because we can write this as 10 times 2 to the third to the t, which is 10 times 8 to the tth power. I will also point out, just because it's often, oh, sorry, you can't quite see that. I will also point out, because it is a question, this is not equal to 80 to the tth power. So they actually are the same, just written in very different ways. Yeah.
If this is a test question, would all answers be acceptable? Or
So, I mean, it really, again, I'm not the one writing your test, so that question really isn't a good question for me to answer because I don't know how your instructor feels about that. But often when we're asked about exponential growth and decay, usually you're asked to find like the C and the K value and write it in this way. But yeah, so I'll say some people teach it more like this, where you're writing the base as 2 and then the power is kind of this multiple of t. And sometimes people do it more like this. I don't, and your instructors might be doing it in different ways. There's not a good answer here, unfortunately. Let's talk more about logarithms and exponents. Yeah, we got enough time. Fortunately, I'm not going to get to the thing I was hoping to get to, but it's life. So, logarithms and exponents. And more generally, inverse functions. Let's see, where am I here? Let's go there. Yeah, sure, you're fine. Sorry, there's a note I needed. Where there you are. Cool. So as I was saying before, inverse functions undo each other. That's kind of the biggest thing to know about them. Here is one of my favorite examples. Yeah. Example. F of x equal to x to the third and g of x equal to the cube root of x. These two functions each undo exactly what the other one does. For example, f of 4 is 4 cubed, which is 64. And g of 64 is the cube root of 64, which is exactly 4. So if we do these both in consecutive like application, if you were to look at, say, g of f of 4, you would get g of 64, which is 4. So literally, you end up back where you started if you apply both the function and its inverse to whatever the input is. So what we say here is that f of x and g of x are inverse functions. Make sure I write this down precisely here. If and only if, people often abbreviate this as an if with two f's. By the way, in case your math professor ever writes that, that's what they mean. What that just means is both directions of the implication are true. Meaning, if they're inverse functions, then the stuff I'm about to say has to be true. And if the stuff I'm about to say is true, then they have to be inverse functions. Both directions of implication are true if we say if and only if. It's also the way we say the definition. If and only if both f of g of x is equal to x and g of f of x is equal to x. That's what it means to be an inverse function. That each function undoes the other one, no matter which way we compose them. Usually, the order of composition doesn't produce the same result, right? The two functions we did earlier in class today were f of g of x, where when we compose them the opposite way, you definitely didn't get the same result. That's not the case for inverses. Inverses, when you compose them the opposite way, you still end up getting just x. Sure. Some things that are interesting about inverses are the following. Yeah. So thing one, we usually call the inverse of f, well, we call it f inverse, but we write it as f to the negative 1 power of x. But you shouldn't say those words I just said. They're terrible. When you read this, we read it as f inverse of x. There's no other good way to say it. And the other thing I was going to say was inverses have, I should say, inverse functions are reflections of each other across the line y equal to x. And why would I try to graph it when I can show you the graph? Because if I try to graph this one, it's just going to not look pretty. But let me show you on Desmos relatively rapidly here. It's got a million tabs open here. If I were to graph y equal to x cubed, and then y equal to the cube root of x, or x to the 1/3 power, they are definitely mirror images of each other across the line y equals x. If you took that red curve and flipped it across the blue line, it would become the black curve, and vice versa. That is always true for inverse functions. But I'm not good at graphing it, so might as well show you the graph that's nice as opposed to try to graph it for you. Like, well, it's pretty good. Other things to say. 10 more minutes. All right. Yeah. So a little while ago, we talked about the function f of x equal to 2 to the x. And we listed some inputs and outputs. I'll remind you what they were. We had some inputs that were like 3, 2, 1, 0, -1, -2, -3. And the corresponding outputs were 8, 4, 2, 1, 1/2, 1/4, 1/8. So here's what I think you should take to heart. Inverse functions literally interchange the role of the input and the output. Right? In fact, we can look back at that graph for a second. Where'd you go? Keep hiding from me. Right? This black graph here has the point, for example, 2, 8. It's on there, I promise. There it is right there. And if they're inverses, the red graph better have the inverse point, 8, 2. And it does. So inverse functions literally come from interchanging the role of x and y, input and output. So what we'd really, really like is a function that is the inverse of this, where instead of the inputs being these numbers and the outputs being those numbers, we interchange their role. And we're going to give it a name. The inverse function here is equal to log base 2 of x. Logarithms are never my favorite thing. They're kind of funky. When I read this, that's not actually what I say in my head. I don't say log base 2 of x in my head, but you definitely should say those words out loud. Log base 2 of x. All 5 of those words are important because the base reminds you, oh yeah, it's the base, and the of reminds you it's a function. So what we're doing here, in fact, here's what I would actually say. My favorite way of thinking about this is saying, well, 2 to the third is equal to 8. That's equivalent to saying log base 2 of 8 is equal to 3. Or if I was actually reading this to myself, I would be saying 2 to what power is equal to 8? Oh, it's 3. So when you're finding a logarithm, what you're really finding is the exponent that you have to raise the base to get the value that's the argument. So when I write log base 2 of 8, I'm saying 2 to what power equals 8? Or if I was writing log base 5 of 25, I would be saying 5 raised to what power or exponent is equal to 25? The answer is not 5, right? We're not looking for 5 times 5. We're looking for 5 to what power? Oh, the answer is 2, because 5 squared is equal to 25. So when we go between logarithmic and exponential equations, we kind of think about going from, say, y equal to b to the x is interchangeable with log base b of y is equal to the exponent, which was x in that previous equation. But again, when you read a logarithm, what you should really be saying to yourself is the base to what power equals the argument. Sometimes it's nice and easy, sometimes it's terrible. A couple more examples. Sure. Yeah. About log base. Sure. Here's an annoying example. Log base 4 of 8. 4 to the first is 4. 4 squared is 16. It's neither of those, right? The answer isn't 1. The answer isn't 2. 4 to what power equals? Well, so if I don't know, I'm going to do some work. I'm going to say 4 to the x is equal to 8. And then if it's an option, not always an option, but if it's an option, we can rewrite both sides as powers of a common base. 4 is a power of 2. 8 is a power of 2. So we can rewrite this equation as 2 squared to the x is equal to 2 to the third. 2 squared is 4, 2 to the third is 8. And then, oh shoot, I forgot to plug in my computer. Terrible. That's really smart. Sorry, this dies. We'll all be unhappy. At least I will be. Maybe you all will. I don't know. Okay. There we go. Safe. So you can rewrite this as 2 raised to the 2x power equal to 2 to the third. And then if you have an equation where the bases are the same and they're equal to each other, the powers have to be equal to each other. The only way those are equal is if 2x is equal to 3. So 2x has to equal 3, which means x has to equal 3 divided by 2, or 1.5. So the log base 4 of 8 is equal to 1.5, or 3 divided by 2. Interesting. So a few properties of logarithms and of exponents. Exponents you're probably more familiar with. We have the additive law of exponents, which we already talked about, where if you have something raised to a power times the same base raised to another power, what do you do with those powers? We add them. There's also like a subtractive law of exponents, where if you have, say, b to the x divided by b to the y, you subtract the exponents, you get b to the x minus y. And then thirdly, you have b raised to the x raised to the y power, a power to a power, you get to multiply those powers. And that's b raised to the power of x times y. I think there's one other one I want to say. A couple other things I'm just thinking of. B to the 0 is equal to 1. B to the 1 is equal to b. It should be noted that in general, our base should be positive and not 1. Okay, there's some corresponding logarithmic things. So if we have, where'd you go here? Yeah, I went right that way. If you have the log base b of m times n, it's equal to the log base b of m plus the log base b of n. So if the log of a product, it's equal to the sum of the logarithms. Basically, you're breaking this up as the addition of logs. Or if you have log base b of m divided by n, we're going to break that up as the subtraction. Log base b of m minus log base b of n. And thirdly, if you have the log base b of m to some power, that power gets to come down in front and multiply. It's p times log base b of m. And I would love to say more, but I'm out of time. So one thing, just one thing. On Canvas, in fact, let me just show you instead of saying it. So in our Canvas, maybe I can show you. There is a video I made a year or two ago about how to deal with the log, semi-log stuff, where you have to like take some data that's been given to you and determine if the relationship is linear for a log relationship or a semi-log relationship, which I know we're not there yet, but you might have to start working on over the weekend. I did make a video of that, kind of going over how to approach it, specifically using Google Sheets, which I think is probably the way you should do it. So if you look here in the modules, right there, how to determine if a relationship is log or semi-log, I would encourage you to click on that and check out the way to do that. It's pretty straightforward once you've done it a few times, but it does take a little bit of getting used to before you've done it. So we'll talk about that on Tuesday.